there might be more people since the test is so.
Oh, what's that? They're probably all the same.
Right, for today, this is a attendance question. So let's find the derivative of ln of secant x plus tangent x. So do it yourself, and then we'll look at it together. Alright, so we're finding the derivative of the ln function, and remember, what was the derivative of ln? 1 over the whole inside, right?
Okay.
So if you want to take derivative of that ln, it's 1 over whatever was inside. The derivative of ln x is 1 over x. But if you have something else in there, for example, if you find the derivative of x squared plus 1, right? This function's derivative will be 1 over x squared plus 1, and then you have to find the derivative of the inside of 2x. Multiply by 2x. So now back to this question, you can find the derivative of that ln is 1 over secant of x plus tangent of x. So you still have to have that 1 over the structure of the division. It's caused by when you're differentiating ln. Right, but that's not all. And then you still have to multiply the derivative of the inside, right? What's the derivative of secant? Do you remember? Secant times tangent of x. What's the derivative of tangent?
Secant squared?
Secant squared. So plus secant square of x. So that's really the derivative. We will first differentiate the outside function, then differentiate the inside function. Then we're going to take a look at all these choices. None of them look like this. All right, so what we can do is try to figure out if maybe there's something we can simplify. The secant, they both have secant, so secant seems to be a common factor. But before that, let's see, this is a 1 over a function multiplied by another function. You can multiply this function with a 1. This is actually secant of x times tangent x. You can move this over to the numerator just so the writing will be easier. This is over secant of x plus tangent of x. So whenever you have a 1 over as 1 over a fraction as 1 over something multiplied by a function, this function is going to be multiplied into the numerator, kind of like this. If you have 1 over 3 times 5. This is actually 5 over 3. Just try to combine so that the representation is a little bit shorter. Okay. And then let's try to think about simplification. This does not look any of, so we have to decide there may be some space for simplification. That's the same with multiple choice. Multiple choice questions are easier, but it's really targeted to a certain format. It doesn't really allow a lot of freedom for how do you want to express your answer. So we have to convert it to one of these form or equivalent of, make the equivalent form. We both have secant, so I'm going to factor the secant of x. And after you've taken the secant of x out, so this first one, you're going to have a tangent of x. And if you take a secant out, which is this, tangent plus secant of x. All right, and this is over secant of x plus tangent of x. Right, that's the denominator. So at this point, we see some common factor, right? You see? The numerator and denominator have common factor. After you cancel the common factor, what do you have left? It's just secant. All right, so we have secant of x. And that is a derivative. So this is one of the tricky situations that you started out with very complex format, and after a couple of algebra changes to it, it looks like a very complex. So it's a tricky question where the final answer actually is simple. So this is the kind of situation we are not being able to predict the format of the derivative. For this one, you have, you know the 2x derivative x plus 1, so you kind of predicted we got 1 over, this must be ln, this must be the inside. So it had that format of the derivative of ln function in there. This is a format of whenever you have ln of a function. We're able to simplify it. There's not, this one, we can't simplify that one. We cannot simplify it. So there are situations that simplification access a really big change. I mentioned this because later in section chapter 5, we'll talk about antiderivative. That is sometimes the derivative of this is this. So the antiderivative of this is this, right? So for example, the derivative of sine of x is cosine of x. So if you want to do reverse, then the antiderivative of cosine of x is actually sine of x plus a number. So this is a backward process. This is differentiation. No, this is integration. But then you see the antiderivative secant of x, that being the derivative, would equal to logarithm of, will be that function plus the tangent of x. And this is something that people always have a hard time, because you have to do a lot of changes in order to figure out, hey, that one has this derivative. We know we had a quick reaction to this. If that was the derivative, then this must be sine, because derivative sine is this. But now in this case, you have to know what kind of function have secant as your derivative. That's a little hard to figure out. Any questions?
Are there gonna be questions like that on the test?
Not on this one, but this is chapter 5. So we will go over this in chapter 5. I just want to say that in chapter 5, after you explain this is this all over again. So hopefully we'll have some vague memory of the time we were in chapter 5. But I'm just saying sometimes the process is straightforward, sometimes it's really tricky, sometimes it's really a twisted process. Okay. So the answer to the question, I hope you already knew, space in this question, and the answer should be, a differentiation is always more systematic. We have a way to handle it since we are learning accumulated formula. But the process of trying to, do you have your cards there?
Yes.
Okay. So yeah, so tomorrow is the test. Today we were supposed to get ready for the test. If you have any questions, if there's no more questions, we'll talk about Super-1. Right? As you mentioned, we should start working on the formula part. Okay. How many of you already made some formula? Let me see your formula card. Yeah, front and back. So you had all the inverse shape this. But I have to say, we rarely use inverse derivative of inverse secant or inverse cosecant. That's really and since
Now, I'm sure whether.
okay, yeah, we're trying to get ready for the bonus question. Okay. So these are the question that you feel like is necessary.
Yeah, I just wanted like the,
Yeah,
like I didn't, because,
okay. So what will be a best format of it? Well, it looks like for you, it's a derivative formula.
Yeah.
Let's see. So maybe we're gonna make a chart. For example, you can. Chart. Alright, so you can make a chart, one column representing the original function, the other column representing the derivative function. So this is a f of x. And this is a derivative of the function. For example, I don't know if you already, I didn't see the trig function differentiation. I see the inverse trig on your column. But do you already know all the trig differentiation? For example, derivative sign is cosine. So if you already memorized it, maybe we don't have to write it on the formula card, but it's something that you do not clearly remember, then we should write it down. Derivative of cosine is negative sine. And then derivative tangent is secant squared of x. Derivative cotangent is that. I should type this computer is hard to type. Negative cosecant squared of x. And then we just did the secant derivative secant is secant sine tangent. Derivative cosecant is negative cosecant of x times cotangent of x. Okay, so these are some of the common formula, and then we have derivative of power function. That's the power is moving the power to the front, and then power minus 1. And then derivative exponential function is the exponential function itself. And then derivative ln function, ln of x, is 1 over x. These are some of the most common differentiation formula. And then the not so common one, I guess, make the chart bigger. Original function, derivative function. All right, the sine inverse, derivative sine inverse is 1 over root of 1 minus x squared. Derivative cosine inverse have a similar structure. This is the original function. The derivative function is negative 1 over root of 1 minus x squared. And one other one I think we should remember is the tangent inverse, also called arctan. Derivative of arctan is 1 over 1 plus x squared. All right, this is all the formula I think. It would be helpful. I mean, I didn't have a secant inverse and cosecant inverse. Let me see your formula card.
Logarithm, private logarithm.
Okay.
It's like someone smaller.
Yeah.
I just wrote a bunch of stuff down because I was like, I'm worried that like my head will just go blank. That happened to me with the first test. Like I did well, but like it was like a good like 5 minute stretch where my head would be blank out. Oh, and that's why I kept on asking what time, how much time we had to go in my head. Time was going a lot quicker. And I was just like, blanked out. So sad.
Yeah, I saw your formula. So if you have a function in the E function, then according to what we are saying, the derivative exponential function is exponential function itself. But if you have an inside function, you have to multiply the inside function's derivative. Right? So the inside function causes an extra multiplication to multiply the derivative of the inside function. But other than that, the e to the g of x does not change. We're using the entire root of x as a factor, so we don't differentiate there, we keep everything there. A similar thing is if you have an ln of a g of x, using g of x as a notation for the inside function, according to the ln function, the derivative of ln function is 1 over the inside. Right, this structure is caused by the ln, but we still have to multiply the derivative of the inside function because it's changing. Right, that way it's more versatile. G of x can be any function, so this is more of the actual abstract formula than an actual differentiation. I also saw that you have the a, so if we have a to a power like g of x, then this is the exponential form, a being a number. So the derivative of this will be a g of x there. This is a exponential function still. And you have to multiply ln of a because that's not the base e, so we have to do the extra term. The proof of that was chain rule as well. And then we have to multiply the derivative of g of x. Okay. You can actually compare this one with this one. We compare, they're similar. The only difference is the base. Anything else? And then we also have implicit differentiation. That is, if you have a function that's given by equation, not by a formula, by equation, then you want to find the derivative, you have to differentiate both sides of the equation. That's more of an idea instead of a formula. Anybody else have other suggestions for formula? This is subject 2. If you don't remember, maybe you should also put down the definition for the derivative where f prime of x is equal to limit of, so the definition that is 2.1, section 2.1, f prime of x is equal to f of, this is a function, this is a division, f of x plus h minus f of x divided by h. This formula allows you to calculate the derivative of any function. That one, if you forget, maybe you should. Right, just want to say if I'm making the formula card, this will be something like that. Any question?
You get like a problem using the last one because I kind of forgot how to use it.
Oh, we ever use it? I think I had a question on the first test. Maybe I didn't put that question, that kind of question.
Well, the derivative using like the long way.
Yeah.
Oh,
I think it did.
Yeah, it looks like none of these questions, we go through all these questions yesterday.
Because we have the power rule, so
Yeah.
it's a puzzle.
Like 2 days.
So it looks like we don't have to use that definition. I assigned one of the test questions
We don't have
for
to use
this, test 1. So I didn't put a question for this, the definition of test 2. We don't need it. I mean, if we're only just focus on the test. Any other question?
Oh.
Yes,
Can we go over one of the homework questions?
okay.
Number 6 on 2.4.
Never mind.
Yes. We did it in class together one time. You want to look at your version of it? We have. Yes. Okay. So let's see. This one. It looks like your version is already done. Problem 6. Well, 6. Okay. So we're over with the formula part. Yeah. So let me introduce this. So I'm using the floor. So here's our question. So the question is calculate the derivative at a given point. So first you have to find the derivative. It looks like it's a division, so we will apply quotient rule. So according to quotient rule, we'll find we'll square the denominator. And then the numerator should be differentiated. If I do it a little bit faster, the derivative of the numerator will be 12, right? 12. And then we multiply the denominator, that's sine x plus cosine x. And then minus, this time we're keeping the 12x. But we're finding the derivative of the denominator. Differentiated denominator, right? Derivative of sine is cosine. Derivative of cosine is negative sine. Yeah, I realized I didn't put the quotient rule, the product rule, all the rules on formula, right?
No, but it's okay. We kind of figured that those are.
Yeah,
be
the
around
rules
that
should be there, and there's also chain rule, so product rule, quotient rule, chain rule. There should be also on the card.
Just.
When I was using the quotient rule, I was like, we didn't put the quotient rule on the formula card. But try to revise the formula card as you work on more and more questions. You realize, hey, this should be on the formula card. That should be on the formula card. So try to make your own card as early as possible today, so that tomorrow you'll be able to apply it. So that's the answer for the derivative. And what we're gonna do is plug in 2 pi. So we will have f prime of 2 pi. We are using 2 pi to replace x. So we have 12 sine. You can just do this sine 2 pi and put all these as your answer plus cosine. 2 pi minus 12 times 2 pi. And then cosine 2 pi minus sine 2 pi. This is over sine 2 pi plus cosine 2 pi squared. So you can actually enter the whole thing as your answer. Because there are a couple of numbers which should, sine 2 pi actually equal to 0. So this is 0. This is 0. And that is 0. Okay. And then cosine 2 pi, you can check with your calculator with reading measure. Cosine 2 pi equals 1. So that's 1, that's 1, that's 1. Okay, so then what we have left is 12 times 1. This is 12. 12 times 2 pi is 24 pi. And then there's 1 minus 0, which is also 1. And the denominator is 1 squared, that's also 1. So then that would be, so that way it's shorter. You just calculate 12 minus 24 pi as it is.
Mostly the ions.
Okay, yeah. Pi is just a number, it's just a special number. This, you can actually enter pi as part of your answer. You just enter 12 minus 24 pi. And that's pretty much how you can just type a letter lowercase pi. Any other homework question? Yes.
I do have problem 3 and 2.5, and I can't figure out why.
2.5. Number 3,
Three.
that is chain rule. You want to look at your version of it?
I would have, yeah.
Number 3. Originally, how did you do it? I remember there are two methods. You can do it by simplifying the logarithm, then find the derivative, or you just go ahead, find the derivative.
I was trying to use the chain starting with the derivative L and then the
Okay.
derivative of the square root.
I see. Yeah, so we'll just go ahead and apply the differentiation. So if you differentiate from the outside, because of their ln, so it's going to be 1 over, right? 1 over all inside is 1 over root of ax minus 2 times 7x plus 7. That's that. Okay, and then the second layer of the function, because of chain rule, is the root sign, right?
Mhm.
Derivative of root function, so here is, you have square root of the derivative of square root function is 1 over 2 times the square root.
Yeah.
This can be proved by 1/2 power. This is a 1/2 goes to the front, and then power is 1/2 minus 1. This is a negative 1/2 power. So because of this formula, we would have 1 over, the derivative of the root part is 1 over 2 times root of the whole inside, 8x minus 2, and then 7x plus 7. That is because of the root function. And then lastly, we will try to differentiate inside this function.
I tried to do that with power rule, but it apparently didn't work out for me. I
Okay.
don't know if I did something wrong or what.
That's actually a multiplication, right? The inside is 8x minus 2 times 7x plus 7. If you try to find the derivative of this, you do product rule. You find the derivative of this part, which is 8. Multiply the second part, right? Plus, you will keep the 8x minus 2. We're gonna find the derivative of this part, that is 7. That's the derivative.
Yeah, I tried plugging that in, but it didn't work for me.
Okay, let's see, this is 56, right? 56x. This 8 times 7 is 56. Now this 8x times 7, that's another 56x. And then this is minus 2 times 2, this is minus 14. This part. We can enter all of that. Let me see what did you enter. 1 over the whole inside and 1 over the part. So you have to multiply that extra. I see that you entered this one and this one. So this is the last piece that you need to multiply, right?
Yeah, I tried plugging in 8 times 7x plus 7 plus 8x is minus 2 times 7, but that didn't.
Let's
plug in
see.
for it.
So 8 times 7x plus 7 plus 8x minus 2 times 7.
You said an extra one on the end.
Okay.
There's my problem. I forgot the parenthesis.
Okay. So it's a parenthesis. I see.
That explains
The
so
last pair of parentheses, the outside part. Okay. The reason that we enter a parenthesis, extra parenthesis there, because this entire thing is one number. Where like this is a number, and we multiply that big number. If you do not have the parenthesis, the computer will multiply this one, and it doesn't multiply the rest. Yeah, they just that.
that makes a lot of sense. Thank you.
Any other question? All right, So we got a little bit more time left today. Let's try to finish.
Yes, actually, I do have another question. Actually, I do.
Okay,
Sorry. 2.4, but it's number 9, but I have my answer. I just don't know if I put it in right. I mean, the answer might be wrong, but like I got my answer a long time ago, but I never figured out how to like
2.4, number 9.
number 9.
Okay, you want to look at your version?
Yeah.
2.5, number 9.
2.4, number 9.
All right. Let's see, what did you answer? According to quotient rule, we'll square the denominator.
Mm-hmm.
The denominator is 2 plus x squared. You have 5.
Oh, what?
Okay. So let's see if we switch that one, it would be,
Oh my, slippery.
that was 2, right? Denominator
Yeah,
is
bro.
squared. Yeah, that's the only thing that was wrong. So it's a 2. Well, it happens sometimes we accidentally copy the wrong number. Okay.
Yeah, and writing it down, 2 and 5 can get mixed up if you write them early.
Yes,
Yeah.
dude, like that's probably what it was, honestly. I also have another question.
Sure.
Over 2.5, 8.
2.5, number 8. This one?
Yeah.
Okay. First question is to plug in the u. We're plugging the g of x, which is x of 7, into the tangent u. So we're replacing the u by x to the power 7. So it looks like this. So it's tangent u. Well, we don't write u, we write the g of x. G of x is x to the power 7. So the first one would be like that.
Okay.
And the second one is f prime of u. You see the second one is differentiating the f of u. So that one prime this, right? So the second function is really all about the u function, not about the g function at all. So we only look at that function by itself, and the root of this will be secant squared u.
Yeah.
So then the second one is if you differentiate the function, you will have secant square u. And that's the second one. And then the third one is a substitution. It's f prime u is having u there, but instead of having u there, we replace it by g of x. Now g of x is x to the power 7, so instead of u, you replace a u in your second step by x to the power 7. So it looks like this. Secant square, instead of u, we write x to the power 7, since that's supposed to be the g of x. And then the next one is g prime. That is only differentiating the g of x, and it's not about the outside function at all, only about the inside. You find the derivative of x to the 7th, which is?
Is it 7x of 6?
Yes. So this one you will just write in 7x to the power 6. All right, last one is combine. Using the chain rule, we're supposed to differentiate the outside, multiply the differentiated inside. So you multiply this one and that one. That's your last.
Okay. And you actually work it out, or can you just put it in there? And
You can just put it in there that way.
Okay.
So it looks like this function multiplied by this function. I'm copying and pasting. This is already in the correct format. Any other question? The 3.1 we just started, the main idea in 3.1 is that we are able to use derivative to identify possible location of the maximum. So first we define what is the maximum value, what is the minimum value. There are actually a y value that is higher than all the other points, or a y value that's smaller than all other points into. Okay, so they're both being called the extremum, and we have this result saying that if you have a closed interval and you have a continuous function, you can always find the maximum. So it's guaranteed, and because for a closed interval maximum always exists, we want to find a systematic way to determine the value. So we have a couple of examples. This example, if you graph it, we realize the maximum value happens at the boundary, at the the right boundary of the interval, the minimum value happen at a critical one. This is when the derivative equals zero, that is a tangent line that's horizontal. So we kind of see that so then we have some idea that maybe whenever the derivative equals zero is important. So we are defining them with a special name. We call them the critical value. But whenever the derivative equals zero or the derivative does not exist, those are very important points. And those important points, we call them the critical number or critical value for the function. Right, so we say that if you got a function that has a relative extrema at a point, then this number must be a critical value. Right, so I think we did this question last time. This is a polynomial example. The minimum happened at x equals 1. That was when the derivative was 0, and the maximum happened at the x equals 3. The maximum value is 40. Okay, so we devise this procedure that if you want to find the maximum value and minimum value of a continuous function on a closed interval, it's a really high requirement. You gotta have a continuous function, you gotta have a closed interval. Now, there are a couple of things you have to find out. You have to find out the endpoint, like A or B. You have to find out the critical number, which could be when the derivative equals 0, could also be when the derivative is undefined. So once we find those x value, being the endpoint or the critical value, you can make a list of all those x values and then calculate the y value for each x value, compare them. The highest one is the maximum, is the lowest one. Okay. That way we have a plan. And we did this question last time. I did graphing and differentiation. Right. And this is one of the example. More example. Let's see this time. This is a trig function. We have a couple of trig functions in the assignment, and people always tend to have slightly more question whenever there's a trig function involved. But nevertheless, sine and cosine, they are defined for any x value, which makes them a continuous function all the time. Because x squared is defined for any x value, cosine is always defined. So this function is continuous on the entire interval. And then we choose a closed interval in the middle, -2 to 2. We want to find. The calculation is already on the board, but we're going to provide some steps. Here. Okay, you can essentially graph it to get a better understanding of the behavior of this function in this interval. But instead of doing that, we will follow our calculus method. So first thing is that we would, number one, we will find the critical points. What are the critical value? Critical value is when the derivative equal to 0 or when the derivative does not exist. In this question, like I said, is always well defined. We do not have any E and E point. So what we're going to do is we are going to find the derivative and make it equal to 0. So this function, the derivative is equal to, the outside is a cosine, so the derivative of cosine is negative sine, and you still have to have x squared by the square. And then you also have to find the derivative of the inside function, which is 2x. So that's how it looks like. Negative sine x squared is derivative of the cosine part, and derivative of x squared is 2x. Derivative of the outside function multiplied by the derivative of the inside function, and that's the derivative. We're setting this equal to 0. and we're gonna try to find the solution. The nice part of it is that, like I said, there is no undefined point, so the only thing we have to do is to make the derivative equal to 0. And then there are two things, there are two numbers. The sign is a number. The 2x is another number. There's only 2x, so this is multiplication. And for multiplication to equal to 0, there are two possible way for it to equal to 0. So either the sine x squared for 0, or the 2x equal to 0. That's fractures, right? A times b equal to 0. Either a equal to 0 or b equal to 0 is the rule. Right? When you are able to factor equation and always provide a smaller, easier way to solve the equation, this is the second one. If the 2x equal to 0, the solution is automatically x equal to 0. But if sine x squared equal to 0, that is different. This is about solving the equation that has a trigonometry, and this is where everybody are having a little bit issue. When does the sine equal to 0? And let's look at the sine behavior. A sine function is a curve. So sine is start from 0 because sine 0 equals 0. And goes up to 1 and then move back down to 0 and then to -1 and then back to 0. That's one cycle. The sine value, you can look at the behavior of sine function on a unit circle. All right, the sine is a y value. You got a unit circle. Sine is a y, this is 0, so this is 0. And then move back, this is 1. The y value on the unit circle. And now this is 0 again, and this is -1, and then back to 0. So that's the cycle. And then this cycle goes on and on. These are all the sine value, and that's why we say that it's periodic. So it goes 0, 1, 0, -1, then 0, 1, 0, -1. It goes out always. So it has a lot of 0. That's the same. Sine function equals 0, 0, 0, 0. There's many 0. And we want to know where those zeros. This is 0, and this is a 2 pi. A 2 pi is when you rotate around the unit circle is in 1 cycle, right? 2 pi is 360 degrees. So 2 pi represents 260 degrees. This is 180 degrees that we apply. So sine equal to 0 in 0, pi, 2 pi, 3 pi, 4 pi, -pi, -2 pi, -6 pi. Basically, any integer number of pi. We have a bunch of 0. We are solving for the 0 in that interval. So we're not solving all the 0 for the sine, we're solving only the one within that range. So x is between -2 and +2. Okay, so now what about the x squared? Our angle here is x squared. All right, the x squared, right on top of it, is between 4 and, well, not -4, right? -2 squared is still 4, but right in the middle we have 0. So x squared is bigger than 0 or smaller than 4. So x squared actually between 0 and 4. So that is, if you are solving for this equation, the x squared as the angle value is between 0 and 4. Where is 4? 4 is, that 2 pi is 6.28. And then pi is equals 3. 3 is, the 4 is over here, right? So essentially for this equal to 0, there is 1 and 2. So basically x equal to x squared. X squared equals 0, or x squared, the angle equal to pi. That's the 2 that provide the actual 2. I hope it kind of makes sense. We're basically searching for where can we make the sine x squared equal to 0. So I'm drawing the sine function just to understand where can we make the sine value. Okay, the sine value equal to 0 only when the angle equal to an integer number pi. So this angle can be 0 pi or 1 pi. All the other ones are not in that instance, so we don't have to worry about it. And so then now that's our solution. X squared equal to 0, then x equal to 0. Essentially, we have two solutions. X equal to 0, and then if x squared equal to pi, then x equal to root of pi. All right, so now we know all the special values that we have. X squared equal to pi, x equal to positive or negative root of pi. So we find the three critical points. So now we're listing our interval. We have -2 and +2, and let's make the +2 there. And then we also have negative root of pi and 0, and then positive root of pi. And that's kind of the reason that we got that table from, because the table involved two of the endpoints, so endpoint of the interval, three critical values. Those are the critical values that will have the derivative equal to 0. So add those three numbers, the derivative is 0. And now that's our candidate. So step 1 in finding the extreme value is to find the critical value. And step 2, once you find the critical value, you want to calculate once you have the table, you calculate the y value. And now you will have to use your calculator. That's plural because we actually have a bunch of y values. So we will plug in x equal to 2, plug in 2 here, that's cosine 4, which is negative. And you can plug in the positive 2, they're the same, because x is being squared. This function is really symmetrical. If you plug in negative root pi and positive root pi, you will be getting the same number. Cosine pi actually equal to -1. -1, cosine 0 equals 1. And then we can see the maximum is 1 and the minimum is -1. So we find out the extreme value for this cosine function is -1 and +1. Any question? These are actually the natural boundary for cosine. Cosine is a function that oscillates between negative and positive. So it's only natural, the maximum is 1 and the minimum is -1. And that is this question. Based on the table, minimum is -1, maximum is +1. You can also, of course, graph it to confirm the calculation. That is cosine x squared. Okay, and we don't need the whole thing. What we need is x between -2 and +2. So we look in the highest value is at 0. When x equal to 0 is 1, and the minimum value is at this. And this. That's the positive and negative root of pi. So, one maximum. Any question? This is one trick example. Another trick example is this one. Find the extreme value of square root of 1 minus x squared. This is actually an equation of the upper half of the unit circle. And the extreme value for this function is actually very straightforward. If you realize this is actually an equation of the circle. Okay, so basically in this question, we have y equal to square root of 1 minus x squared. This is a really important function because we see this all the time. You kind of relate it to our unit circle. So this is cosine or sine value. So if you square both sides of the equation, you have y squared equal to 1 minus x squared. If you add x squared, you have x squared plus y squared equal to 1. Now, x squared plus y squared equal to 1, that is a circle, but y equal to root of 1 minus x squared have the feature that the y value is positive. For this equation, the y value can be positive or negative. That's kind of the reason that even though we change from square to get this and to get this, when you square that equation, you're adding more point to it. This equation and this equation, the second one and the third one, they're equivalent. They're the same thing. But the first one and the second one, they're not the same thing. So that is, when you square both sides of the equation, you think you are making the equation equivalent, but maybe you are accidentally adding more point to it. So normally that's the thing, when you are changing the equation, most of the time we're not removing any solution, but many time we're adding more things to it. So like, when you square, you actually made the y being positive or negative, but the original equation, a y squared root of x squared only represent the upper half of the unit circle. This is a square root of 1 minus x squared. So that's what does this represent? Okay, and then again, you do square x squared plus y squared equal 1. That's actually the entire circle. So having the graph there, you kind of see the maximum value is 1 and the minimum value is 0, because that was the upper half. So that's visually how do we see it, but how do we see it from calculus points? You would find the derivative. And the derivative of this function is 1 over, this is a root, 1 over 2 root 1 minus x squared. On the outside is a square root function. We have as derivative. We also have to multiply the derivative of the inside function, that's negative 2x. 1 minus x squared, its derivative is negative 2x. So now, again, you can multiply 1 with negative 2x, and you get negative 2x over 2 times the 1 minus x squared. Okay, and the 2 can be canceled, so that's negative x over root of 1 minus x squared. Okay, so that's our derivative, and then let's think about a critical point. This function has a domain of the 1 minus x squared has to be positive or bigger than 0, because you can't take square root of a negative number. You have to guarantee this to be positive or 0. So then the 1 is bigger than the x squared. So x squared is smaller than 1. So then x is between negative 1 and positive. So the natural boundary, which is an interval, negative 1 to positive 1. And you can try all the number, x equal to 2, x equal to 5. They're going to be all defined for the function. So the x value for the function has to be anything between negative 1 and positive 1. So when you're trying to find the critical point, this derivative, we're going to try to find the point where this function is equal to 0 or undefined. Now, if this is equal to 0, a fraction can only equal to 0 if x equal to 0. So that's the only critical point I can think of it. If this one is undefined, the denominator will be 0. If the denominator equals 0, then x minus x squared equals 0. That's when the derivative does not exist. And you can see the function does not have the derivative. It's when at this point, there is no derivative, because that was really the boundary for the function. So that will have x equal to 1 or negative 1. That's when the function is undefined. So anyway, critical point, you got 0, you got negative 1, you got positive 1. The end point, you have negative 1, positive 1. So now, as a table of all the possible maximum, you will be making this chart of the x value. The x goes negative 1, 0, and positive 1. They're all critical point, and also including the end. Now we're going to calculate the value. If you plug in negative 1, you see that this is 0 for that function. If you plug in 0, we have 1. If you plug in 1, you have 0 again. So essentially, maximum is 1, minimum is 0. And we can find the location of the maximum, which is right in the middle, x equals 0, and minimum at negative 1 and positive. Any question? Obviously, the calculus is more complete, more complex, and if you know this is a unit circle and you look at the graph, we can quickly identify the minimum and maximum. So that is, if you are able to memorize some of the common graphs of functions, it helps a lot. It really makes a understanding function faster if you already knew the graph. Let's look at some of the homework assignment for 3.1. Yeah. Yeah. So,
7.
are you already up to 7? Okay. Let's see question number 7. It's a little different than what we've been working on. This one has exponential function, so it will be a little bit more interesting. Okay, so this function has, it says we are looking at the behavior of this function between -2 and between 2 and 0. This question 7 on 3.1. This Chris was looking at. All right, so in order to find the minimum or maximum, the number one thing is to find a critical point. We have to find the derivative. So find the derivative. To find the derivative, we follow product rule. We have a x, derivative x equal 1, right? 1 times e to the -5x. Plus, you will keep the x, you find the derivative of e to the -5x, which is e to the -5x. You also have to multiply the -5, that is the derivative of the inside function. So that's according to the product. Any questions so far? So you can see that's the derivative. We now want to make this equal to 0. So we know how to try to solve this equation. All right, critical point for a function, there are two kinds. When the derivative equal to 0 or when the derivative is undefined. But exponential function is always well defined for any x value, so we don't have any undefined point. So that's why when you try to determine the critical point, this is the only one that you can solve for. We can try to look at this function closer to see if there's anything to simplify. You move the -5 to the front with say plus x, so it's -5x. Multiplications, you can move it over. So it's a little bit tidier or concise. All right, and then we realize this is a function, the equation that has two terms. Both of the terms have e to the -5x. So we can bring the e to the -5x outside. And then we have 1 minus 5x. That's after the e to the -5x is factored outside. Now let's think about how we make this equal to 0. Now, e to any power, it doesn't ever equal to 0. E to the power, e to the 0 equal to 1, e to the negative, e to the 1000 equal number, e to the -1000 is still positive. It's like 0.0 something, but it's really positive. So we know that this first factor, this is the multiplication. In the multiplication, we can either make one factor equal to 0 or make the other one equal to 0. So you can make 1 minus 5x equal to 0. Or you can make the e to the -5x equal to 0. But that one does not equal to 0. For all x value, it doesn't equal to 0. So we can't have that factor equal to 0. So the only 0 has to be the 1 minus 5x, and that will be 5x equal to 1, and then the x equal to 1 over 5. So we find out there's only one equal.
So we,
1 over 5.
oh,
Divided by 5.
Yeah.
Okay, so that's our critical point. So you have a table. You set up a table for x value and y value. It has to have the endpoint 0 and 2. So 0 and 2. Right in the middle of 0 and 2, we have 1 over 5. So now it's time to do the calculation for the y value to determine which one is max and which one is minimum. If you plug in 0 for the x, it's 0. So this one definitely is 0. And if you plug in the 1 over 5, it's going to be 1 over 5 e to the -5 times 1 over 5. So e to the -1. If you plug in 2 for x, is 2 times e to the -5 times 2 is -10. Okay, now we can see that the e to any number is positive. These two are positive number. That one is 0. 0 has to be the minimum. And where was the maximum pin on this two number? Which one's smaller? I believe this is there.
Yeah.
That was maximum. So now we now know the maximum value and minimum value. The minimum is 0. The maximum is 1 1/5 to the -1. The minimum happens when x equals 0. The maximum happens when x equals to 1/5. Right, those are all the answers for this question. Do you have a different number on your question?
Yeah. I was not sure about the problem.
So you can see the process of using calculus to find max mean. Number one, you have to understand the derivative, because sometimes the critical point happens when the derivative is 0. Sometimes the critical point happens when the derivative is undefined. So that really depends on how the function is. Once we find all the critical point, it's evaluation. That's the blue table. The endpoint, the two endpoint of the interval, and then maybe you can find a point right in the middle, maybe not. Sometimes your function does not have any critical point at all, then the endpoint will be the only thing you can calculate. Any questions? All right, we got time. Let's finish one more. Let's start with question number 1. All right, this one has a polynomial of degree 2. So it really depends on how the endpoint is being chosen. So let's work out this one, and we're really gonna follow the calculus with something that's really similar to the practice question and the front point, and then we'll move on to other question. All right, so question number 1, you may have similar question on your question. This first one, it has a really simple derivative. You find the derivative of the function equal to negative 14x. Right, again, the negative 14x is well defined for any x value, so we don't have any undefined point. So we're gonna set it equal to 0 just to find it. Once you set equal to 0, then x equal to 0. That's a critical point. Right now that we have the critical point, let's set out the table. The x value are -5 and 2 and then 0. So -5, 0, and then 2. We're going to try to calculate the y value. Not the y prime. Y value is the original function value. We put in -5, -5 squared is 25. So that is 3 minus 7. Which is 7 times 25, 175. So this is actually -172. When you plug in 0, then you get 3. If you plug in 2, that is 3 minus 7 times 4. 8, 3 minus 20, -25. Okay, after we calculate all the y value, we realize that the maximum is the only positive number that's maximum. The minimum is the one that's really, really negative, -172. So now we have the maximum is 3. The minimum is -172. The maximum happened at 0, and the minimum happened at -. So one occur at the critical point, one occur at the boundary. -5 is the lower boundary of the interval. So there we have.
Okay, I have a question about the first part. How did you get the negative 14x?
It's the power rule, right?
Okay.
We're finding the derivative. 3 has your derivative. 2 times the -7 is.
Okay. Sorry, I just missed that part. Okay.
Yeah, that
makes
one
sense.
is calculation of the. Yes.
We'll go to question 9.
9, okay. Let's see, my answer is late. Okay, so that's the first question. Question 9. I have a logarithm, okay. Let me copy the question.
The other ones were pretty like, the left. It's all the meaning algorithm.
Okay, which one?
Like this one. Unlike the other ones. just one out of trouble.
Okay, yeah, let's look at question 9. As usual, we're using calculus, so number one thing, we will find the derivative. Derivative of the x equal to 1, the ln of x is 1 over x, so minus 3 times 1 over x, which then equal to 1 minus 3 over x. Okay, now this function, it's undefined when x equals to 0, but our interval does not have 0. Therefore, on that interval, we don't have any undefined point. There's no undefined point. The only critical point is when this equals to 0. If we want to always keep in mind the critical point is when the derivative equals 0 or when the derivative is undefined. So you always have to rule out the fact that this function might be undefined. It's defined all the time, so now we're solving this equation. Set it the derivative equals 0, and now we're solving it. In order to solve it, we can move one term to the other side of the equation. You have 1 minus 1 equal to 3 over x. So let's add that to the other side of the equation. The reason I want to do this is because there are 2 terms on the left. So if you move one term to the other side, you have 1 term on the left, 1 term on the right. It's easier to work with this equation that way. There's not multiple terms. The right side is the division. So when you have division, you might want to multiply both sides of the equation by the denominator just to get rid of the division. So we multiply x here, multiply x there. Then x will be canceled. We have x equals 2. Right? That means the critical point is when x equals 3. Are we okay there? So that's pretty much step 1. We find out the critical point. And then in step 2, we're making a table of x value or y value. I realize I can make the x horizontal line. X is from 1/3 to 7. We find a critical point at 3. The 3x value. Calculate the y value. Now, if x equals 3, it's going to be 1 over 3 minus 3 times logarithm 1 over 3. I have no idea what that number is, but it's not very big. If x equals 3, it's going to be 3 minus 3 times logarithm of 3. This will be 7 minus 3 logarithm of 7. I have no idea all these numbers. I'm going to have to use my calculator. So do you guys have a number? I don't know. They're all.
The 1/3 one is 3.63.
And the 7 is 1.162.
1.162.
Yeah.
This one?
Like the
3.63.
3.
Right, it was 3.629, but I just went to 3.63.
Okay. And this one? Is it negative?
yes, negative 0.2958.
All right. So basically, based on the decimal value, we realize this is the minimum, and this will be the maximum. Okay, so now we know the maximum is, we have to copy over the whole thing. It's 1 over 3 minus 3 times logarithm 1 over 3. It occurred at 1 over 3, and the minimum is when x equal to 3, and the value is 3 minus 3 times logarithm. So you have to actually the full number. It's question 9. Is it okay?
Yeah, the only other question I have is question 6.
Okay.
I didn't know how to solve it, so I guess you said those. You can see it on the notes, but I
Okay,
actually,
you can see the graph.
yeah, but I actually want to know how to solve it. That way I.
Okay, sure. This is a question 6. Again, we're trying to find the maximum mean. I think this kind of problem, the difficulty is because we got the derivative that equal to, the definition is a trig function, so derivative might be harder to solve. So first we will find the derivative. The derivative is equal to, that's our function. We'll Derivative sign is cosine, so it's 4 cosine x. Derivative cosine is sine, so 4 cosine x minus 4 sine x. That is a derivative. Again, true function sine and cosine are always well defined. Tangent, cotangent, and secant, cosecant, they have all the same point. But sine and cosine are always defined, so the only possible point is when this equals 0. So again, we're solving this equation. Equal to 0. To solve this, you again have two terms on the left. You move one term to the right. You have 4 cosine x equal to 4 sine x. We divide both sides by 4, then you have cosine of x equals sine of x. To make it easy to solve, we divide both sides by cosine of x. All right, that way we have sine over cosine. This is a 1, and this is a tangent. Sine over cosine is tangent of x. So now we need to solve the tangent of x equal to 1. And the easy part of this is we're not solving tangent of x equal to all the number. True function or periodic, this equation has infinite many solutions. But we are only solving the solution between 0 and pi over 3. 0 and pi over 3 is between pi over 3 is 180 divided by 3 is 60 degrees. So it's less than 90 degrees, and this can easily solve with the inverse shape. So x equal to tangent inverse of 1. If you use your calculator, tangent inverse of 1 with degree measure, you're gonna find this equal to 45 degrees. Right? Anybody have a calculator?
Yeah, it's 45.
It's 45 degrees, and therefore it's pi over 4. So we find out there's only one critical point that's pi over 4. That's all because the interval is small enough. There are other solutions, but we're not looking for all the other solutions. But now that's really step 1. Step 2, let's compare. So we have all the x values. They are 0, 0, pi over 3, pi over 4, pi over 3. Now it's time to calculate the y value. If you plug in 0, sine 0 equal to 0, cosine 0 equal to 1. So that is 4. Right? If you plug in pi over 4, sine pi over 4 is root over 2. So 4 times root 2 over 2 plus 4 times cosine pi over 4 is also root 2 over 2. Because tangent equal to 1, when tangent equal to 1, cosine equal to sine. And that cosine equal to sine is our equation. So cosine is also root 2 over 2. Altogether, that makes it 4 root 2 over 2. That obviously is bigger than 4. Pi over 3, 4 times sine pi over 3. You can use your calculator with reading measure to find the decimal number. 4 times sine pi over 3 is 3 over 2. And this is plus 4 times cosine pi over 3 is 1/2. So it's going to be 2 root 3 plus 2. Although I don't know which one bigger. Like 4 root 2 or 2 root 3 plus 2, which one bigger?
It'd be the
4 root 2. Okay, so we find one maximum, one minimum, and so then all the other one, you think you should enter n. It's n for all these. Except we do have a max and mean. The maximum happened at pi over 4. The minimum happened at 0. And 4 is definitely smaller. So the maximum would be the 4 root 2. The minimum would be the 4. So that's really all day. So let's at least say what was the maximum? It happened at pi over 4. Value is 4 times square root of 2. See, at least those are right. And then we have a bunch of n because there are only one maximum, one minimum. we really don't have any of the. Right, and then I remember the minimum happened at 0. This is 0 and this is 4, and that's, at least on my version of it, that's all the solution. Okay, that'll be it for today, but, again, this, you can do it after the exam, and today the main thing is make sure you're ready for tomorrow's exam, have your formula card made, and make sure you add the quotient rule and product rule, or chain rule, tomorrow afternoon, so I'll see you. So that we have another success, kind of like the first one. See you tomorrow.
We're pretty much the only 3-1.
Oh, yeah, there's a clear question over there, and the solution is on the board, just in case you.
I got all of them right except the Y point for the maximum. Mine's the exact same problem except it's just 8. So I put in 8 square roots of 3 plus 4 because mine is different. My 8 square roots of 2 is less, I think.
Okay, it depends on the interval, if you have any negative, the interval, let's go down to the interval. Oh, the power 3, the same.
Yeah. So like this is my 8
There's no, square root 2.
Yeah, so my 8 square roots of 2 is 11. And this one is 17. So that one's higher.
Let's see,
Because it's the maximum, right? So obviously the one that's higher would be.
right, but I still think it's 8 times square
You
root.
just want me to try it? Okay.
Well, you have a graphic from
Yeah.
there. You're basically.
8 times square
I don't
root
use
of
it.
2.
That makes no sense.
That's because if you put square root of 3, there it's not 17.
You gotta write
It's,
down credit.
Exactly.
let's
You
go
plus
down to
risk.
do the
Not
calculation.
getting credit
If you
for,
plug in pi over
getting half
3,
right.
this is 8 times, sine pi over 3 is root 3 over 2. So it's actually 4 root 3 plus, if you plug in root 3
So
over
here, so it'd be 8 square root 3 over 2 plus 8 is 1/2. This is yours, but can I translate it into mine?
yes, but this is the 8.
No, but
This is root 3 over 2, and this is the 8.
Like,
So 8 will cancel
I'll
with
do
2. So it's 4 root 3.
Oh,
yeah,
I'm like,
so can I try it?
like this is what was.
No, it's smaller.
Oh, so once you do that, it's smart. Okay,
It's
I'm just
smaller,
gonna look
yes.
and see what it is.
Yeah, you can put it in to see, because what works kind of like a calculator. Plus 4.
Can I just do plus 4?
Yeah,
Or it won't put it in?
outside. Plus 4 outside, yeah. You see, that's 10.
10, okay.
Yeah, so slightly smaller.
I'm not like perfect, but I can find there's a way I can do it. Oh yeah, here's a table.
What's that?
This is the rules. But of course, it doesn't have the private. But I can find where it is here. So like I can find,
oh, good, you can't graph pi.
not really, unless I think you might be able to change the settings. But yeah. There's another way to, there's another way to find like this. There you go. We can, like,